A part of my responsibilities at the planetarium is presenting to school groups of all ages, writing and presenting live public shows, and training other students. And so that led me into working with Dr. Schultz on this Community Anchor Grant, which we are proud enough to be a part of. And that involves both the Fargo-Moorhead community and our campus. So we have 3 organizations on campus that we are working with. We have an oceanarium on campus, as well as our own planetarium and the Regional Science Center. And all of these are in conjunction with the Fargo-Moorhead Public Libraries to reach a wider audience than just our planetarium could reach. And our main goal is to reach underserved populations in our community. Now, to do this, we are working with NASA's Universe of Learning, and specifically NASA ViewSpace, which does videos and interactives for the public. And specifically, in the middle of that graphic there are library kiosks. This is a project that is still very much in the works. I will get into, I have presented one of my presentations so far for this grant, but I am still currently working on making the video library kiosks for the libraries. And the main goal of this project, because we have such a diverse range of projects being presented, the main focus was water. And the reason for that was to focus on what NASA is doing both here on Earth and also up in space, so we can combine all of our lovely interests on campus into one big overarching show. So using NASA ViewSpace, this is their website, and this is specifically some of the interactives I will be using in the kiosks. Mine specifically are the search for water and where water and therefore potentially life is within our solar system and also outside of it. So working with NASA ViewSpace as a partner, you can get these video libraries that can then be reels that are just played consistently either outside of your own planetarium or in my case at a library. And I'm also hoping I am doing 2 presentations, one of them focusing inside of the solar system and one of them focusing outside of the solar system. I'm hoping for my second presentation, which I will be working on in the coming semester, to also have these reels playing outside of the planetarium just to reach a wider audience. Now, to get into the show that I did, I just presented my first show of water inside the solar system on June 14th, so right before coming to this conference. And what I have on the screen here is the setup that I had when I was presenting. So this is what was on my monitor as I was presenting, and I will show you what was on the screen in a minute. But what we used is we used Illuminati and World Viewer to run our software, and then the main platform that we use to fly around in our solar system is OpenSpace. So over on the left there is what we call the backdoor of World Viewer, and each of the columns is a chapter. So within those, you can click a small eye that is on the top, and then only the pictures and images that you have within that chapter will show up on the dome. And then down in the bottom, there's a green circle. That is how I was able to put any full dome images or smaller images up around the dome. And at least for me, while learning how to use this type of software and create my own shows, this was very useful, as it was easy to adapt to what I needed for this as I was learning. And then the 2 middle rows where you see a whole bunch of eyes, that was OpenSpace. So I had that running the full time I was presenting, and I was flying around live as we progressed through our solar system. And that was also very useful, as I was able to adapt my show in real time. As while I was presenting, a couple kids had questions, so I was able to fly back to things and move forward and turn on and off my pictures to better help explain the answers to the questions they had. Now, looking quickly into what my show was, being about water and where it is on the solar system, I thought it was fitting to start in the ocean. I also thought it was kind of fun because they were expecting space, and surprise, they got water. So we started under the ocean in Belize, looking at fish, and I wanted to accentuate the point that while we are looking for life in the solar system, life on Earth is only possible through the water that we have, and it is all around us. Specifically, looking for life in the solar system is probably more on the microorganism scale. It is not on the walking, talking alien scale. So that is a misconception that I wanted to make sure kids knew about. And so starting at the ocean was very useful for that. Then I went into how we got water on our Earth in the first place, and then talking briefly about flying to the sun, and talking about how we got the elements from the sun, from fusion, and then from stars exploding and going out into the universe, and how that made our solar system, and therefore the water that is on our planet, which includes the concept of asteroids and meteors with water hitting the Earth, which got our water here. And then the final picture I have up is the Goldilocks zone, or the habitable zone, which our Earth is in. And I use that to show that, kind of like the Three Bears with Porridge, there is too hot, there's just right, and there's too cold when it comes to where we can find planets, and that is within our solar system. And then later in the presentation, I looked out beyond our solar system to see where there could be other Goldilocks or habitable zones. And also, as I traversed through the solar system, I came across these NASA travel posters, which were made as kind of like a futuristic idea of, in the future, when humans could travel all throughout the solar system and beyond, where we might travel to. And I thought these were fitting with both the search for life, that we could potentially be the life on these planets in the future, but then also that they brought up kind of the points I was going to talk about on some of the planets before I could even get to them, because like with Venus, it had very thick clouds, and that is the observatory that is on Venus. And then with ones like Europa and Enceladus, which are both moons, they have the underwater oceans, which is the tourist destination in NASA's future. Now, as I moved out beyond the solar system, I talked briefly about James Webb and how in the past year it has been used to look both within our solar system and also beyond our solar system to see if we can find other planets or other solar systems similar to our own, specifically the TRAPPIST-1 here, where specifically planet E is very similar to our own. It's in the habitable zone. And I had a really good conversation with a kid afterwards where he was comparing every single planet to either Mercury or Venus or Earth or Mars. And so that was very fun. But this is the portion of my show that I want to expand. My next show is going to be July 12th, and we're doing that in conjunction with the anniversary of James Webb's first images, which we had a show of last year as well. But I want to combine more of looking beyond our solar system and James Webb and the search for life in that one, so that is where I'm planning on taking the show a bit less in the solar system and a bit further out. And I have here a few live images that were taken for me while I was presenting. We again have the Belize Ocean, but then also one of my final slides, which you saw on my previous slide, which had James Webb and then TRAPPIST-1, and then I also, someone asked about light speed, so I was able to, fortunately, with WorldViewer being as adaptive as it is to live presenting, I was able to bring up an image to help me convey how light travels and how that affects us looking back in time. Now, one thing that, along with what I'm hoping to do, I, for this grant, need to make a second show that focuses on looking beyond the Earth. And this is one of the interactives that ViewSpace has, which I have found very useful when, as I begin to work on that next show, as it shows that TRAPPIST-1 solar system, and it specifically shows where water signs are, and it has to do with how James Webb looked at the chemical makeup of the atmosphere. And so I'm hoping to include those in my future presentations. This grant is going to go through the end of this year, but beyond working on this grant, we're hoping to continue working with the Fargo-Moorhead Public Libraries, as well as the other organizations on campus to continue educating the public on these topics. So I know that was a very brief introduction to everything I have done. I appreciate everyone listening to, and if you have any questions or if you would like to hear more after so I don't go over time, I would love to talk more. Thank you. One question. Yes. Hi.
Amazing talk. When you're using WorldViewer to present live, are you pressing buttons straight out of the composer, or have you used
Yes.
GUIs?
Yes, so I've worked briefly with GUI, and that would be with MJ. We were doing that in OpenSpace, teaser for what is to come. But I am hoping to implement that in the next show, as that would make it much easier to use. I just found it easier with this first show because I was the one who designed the initial interface to just use that. But if anyone else was to present the show, I would make a more GUI interface just so it's easier to use. But for live adaptive presentation, I found the backside of it to be much easier. If I had a more strict presentation where I didn't want to take any questions during the show, I would stick to having a GUI interface or something that was more concrete, if that makes sense. Yeah, okay.
All right, so thank you very much to Emily. Next we have Amy from the Edelman Planetarium and Connor, who are going to be talking about Mars and rovers.
And while Amy's getting this set up, I'm actually going to pass around this wheel. You all can hold it, but I'll tell you the same thing that I tell third graders. When you get it, this is not made of the same material as the real wheel. This is made of plastic. It's not as strong, so please only grab it by the black outside part. Don't pick it up by the spokes, because as I also tell them, it could break, and we don't want to tell NASA it was you that broke their wheel. So I'll get this around now.
All right. Good morning, everybody. I'm Amy.
Yep. I'm Connor.
And we're with the Edelman Planetarium. And today we're going to be talking about our exhibit that we got from NASA called Roving with Perseverance and the activity that we've developed to go along with it. So we're going to cover 3 topics today. First, we're just going to introduce what the exhibit is. Then we're going to talk about how we're actually using it in our programming here at the Planetarium. And finally, what we've learned since we started using that program. So Roving with Perseverance is an exhibit that we got on loan from NASA's Jet Propulsion Laboratory. We got it back in September, and we have it through March 2024. There are a couple different iterations of the exhibit, but the one that we have includes a tabletop rover. It's about a 1/10 scale model of the rover. We have the full-size wheel that's making its way around the room right now. We have an 8 by 10 foot selfie station, the pull-up banner over there, a Mars globe that includes some of the landing sites on it, and then here at the front, we've got our Mission 2020 kit, which includes some touchables that we're able to use, including a bit of the insulation, a parachute sample, some of the bridle, and the drill bit replica. So since getting this exhibit from NASA last fall, we've developed an object-based interactive program that's based on modern museum educational practices. So it's object-based and also inquiry-based. Objects are really great for museum educational programs because they aren't age-specific. So we can cater our program to any age group. We've done it as young as preschoolers, aged 3 and up, all the way to university courses. So it's really versatile for us. Objects will naturally provoke inquiry and emotion, so it can create a sense of awe that helps to bring back your experience and make it a little bit more memorable and make learning more likely to happen. Also, because it's inquiry-based, we can ask open-ended questions that will help to provoke their thought and imagination as well.
And so with that backing, what do we actually do in the planetarium? Well, first we just bring up Mars and kind of ask them what they see or what they notice. We ask them, why is Mars red? Or why do you think Mars is red? Then point out things that we can see on it, so some craters, volcanoes, of course Olympus Mons, the Mariner Valley, and the ice caps. But the main thing is to then show the extent of the oceans that used to be on Mars, and make the connection between water, which we just heard about too, that water means there could have been life on Mars, which brings us right to Perseverance, because its main mission is looking for these past or signs of any past life. So with Perseverance, we then bring up a interactive from NASA of the Perseverance rover. This is just a really cool website. We just display this on our dome and simply ask them, what does Perseverance need, or what kind of tools or equipment should it have to help us learn about Mars? And a few of these might be things they could see, like the wheels, of course. They probably saw that wheel as they walked into the planetarium. Then other things like a camera, like we bring up the mast to show some different cameras, a power source, a drill, and then an antenna or communication system. And as we do this, or I guess what the idea behind it initially was to, I guess, focus on visual thinking, where if we were in a classroom, we would write down every single idea they had and end up with a huge list. This is something we've done when we've done this presentation in classrooms, but in the dome, we just focus on these 5, try and kind of lead them to these 5 main things that we thought of. And as Amy mentioned before too, it says focus on open-ended questions. So once we get an answer, we say yes, we show it on the rover, but then what else? And keep pushing that, what else does the rover need? And then we have the touchables too. You saw some of them. So after they kind of hit those 5 main things, we just pass out, I think, 4 of the touchables, and we do not tell them what they are. We also pass out the wheel, which is a hit with everyone, including everyone here. And once we retrieve the items back, we simply ask them, what do you think the rover uses them for? Not necessarily what they are, but what is their use? And we have some videos that pair with that. So we have a drilling animation from NASA. There's a really cool cinematic trailer of the sample return mission, which is this like orchestral, really epic thing. And we end with the landing video of Perseverance.
So what have we learned since implementing this particular program? Well, to start with the negatives first, we found with really large audiences, our planetarium seats about 100 people. So with really large audiences, there can be a lot of downtime for students as they're getting the different materials. We do try to spread them out. So, we might start the wheel here, the parachute sample there, then we'll go to the back of the room and you get the bridle and you get the bit of insulation. So we do try to pass everything out so that it's all going in different directions and there's more time for people to have their hands on a material. But there often is still some downtime, and we're trying to figure out different ways that we can deal with that so that we can keep everybody engaged and focused throughout the whole program. It's also really difficult to do the inquiry-based portion of the program with really young audiences. I mentioned that we do offer this program for preschools, but for groups that young, they often don't have enough, background knowledge to be able to say, well, we're exploring Mars, we're going to need some cameras, we're going to need a drill, we got to land there safely somehow. So instead of asking them to give us those materials, we just tell them, these are things that the rover will need, and here's the parachute sample, here's the insulation, and we just let them touch it, but don't give them that opportunity to explore what it could be. As for the benefits of it, we found that it really expands our options within the planetarium. Our planetarium is at a university, so we have no exhibit space whatsoever. Getting this exhibit has allowed us to build a little area in front of the planetarium in our atrium that allows people to have something to view as they enter, or to linger around after the show and look at the different exhibits, take their selfie on Mars, and do things like that. Of course, it also extends our school field trips that we offer. Typically, a school field trip would be 1 hour long, but with this program, we can extend it now to an hour and a half, and they just get this extra opportunity to learn and explore and find out what NASA is doing besides just launching people up to low Earth orbit. The really great thing about it, of course, is that it is easily transported. As you can see, we brought half of it with us today. So we've been using it at outreach events. We'll take it to homecoming and other activities around the campus, but we've also been invited to speak at schools as well. And so we can bring our Roving with Perseverance exhibit to these schools or to this conference and start sharing all of it there. And then finally, it's just gotten a lot of really great feedback from everybody that's seen it. Our university has had it since September, so about 23,000 people have seen it, the exhibit, since we got it installed. These are kind of indirect numbers. We don't know necessarily how long they were staring at it or, if they even noticed what it was. But about 23,000 people have seen it. Over 4,000 of them have had a direct contact with it through our programming. They've gotten to touch the wheel, they've gotten to touch the installation. 3,800 of that have been just school field trips. So we're really starting to get a lot of people. We've got it for another year, and we're really excited for the possibilities. So these are things that you can also get for yourself, and if you're interested in the application process or anything else, just let us know. Thanks.
Thanks.
Yeah.
Did you just apply for it? How competitive was it?
Yeah, so we are involved with the NASA Museum Alliance, and there had been a call for proposals sometime, I think February 22, maybe. There was a post about these materials being made available. So you have to fill out, they had a form that they wanted you to fill out to kind of get a general idea of your institution and how you would use it and whether or not it would be a good fit for the rover. And then after going through that initial process, then you have a meeting with the Mars Exploration Program leaders to kind of get a little bit more information. Finally, we had to write a letter of intent to NASA, just sort of stating, these are the pieces that we want. This is how long we want it for. This is how many people we expect are going to get it. And just all of those metrics that they want so that they can build together a contract that then needs to be signed by our university, stating that we're going to be responsible for the materials, and if they break, we're in charge of paying for it, things like that. So.
It's also fairly low demand, right? Because, or at least before today, it was low demand. But originally, we were supposed to return this in mid-March.
Yeah.
But we got an extension.
That's right. Yeah, our original loan was only for 6 months, and they're giving it to us for an additional year on top of that. So we've got it for 18 months total. There is a potential, I think, after that to extend it another 6 months. I think 2 years is the limit that they allow you to keep it. And it kind of depends on whether or not there's other institutions also waiting for it. So. Any other questions?
The Build a Rover website that you used, is that JPL's open source Build It Yourself Rover?
No, it's really difficult to find. It's a NASA interactive. It's already built. And what you can do is you just click on the different parts of the rover, and it brings it up for you. Let me see if I can.
It's incredibly tedious to actually find it on Google, funny enough, but 'cause there's a lot of interactive rover sites.
Any other questions while I try to quickly bring this up? Okay.
I'll scan for hands.
Thank you. Yeah.
With really little kids, do you ever do the human analog of like, what do you need to see? Eyes, hold it over, eyes with the camera.
No, we never have tried that, but that's a good idea. That might be a way to help bring it back to that, make it a little bit more understandable for the younger age groups. Okay.
No, 'cause that's download.
Yeah, that's the download one. It's always. if you go to NASA's Mars rover website, they
Mars
have
2020. That's what you need to Google. Mars 2020 Perseverance Interactive. I'm remembering this now. So when we did it in the classroom, we didn't have the link either, and we were just like scrambling to find it for a bit. I lied. All right.
this one. No, this is a different one.
That was cool though.
It is cool. It's not the one that we use. So we have it actually bookmarked onto our digital system. So we don't even need to remember what the page is, and we're able to just pull it right up in the planetarium. But yeah, it's a really fun interactive. For the exhibit itself, when we received it, we were given a list of materials from the Jet Propulsion Laboratory that we could use to help expand our programming, and that was one of the things that they had listed in there was this interactive, which Connor has just found finally.
You go to Mars 2020, just that website, and scroll down. It says Explore the Rover in 3D. This will take a moment, but we'll quickly show you. There we go. So you can actually like move it around in 3D. You can either click on parts here, if you want to click on the mast to show the cameras. That'll take you, whoa. I normally don't use a trackpad. And you can also select these. So select if you want to like look at the microphones, the suspension, the wheels, you could also select through the menu.
And it'll then highlight those objects for you and give you, small details that they can read to go along with whatever you're describing about that particular feature.
Thank you for providing that.
Yeah, it's like right up here. You should be able to. Probably, yeah. I can do that. I can stay up here with you if you'd like. Of course.
Hi. My talk is the worlds within Star Wars, exoplanets, as well as moons and planets in our own solar system that are analogs to the ones in Star Wars. Next. It all started with Jay Lamb of the Louisiana Museum of Arts and Sciences. He gave a talk during the pandemic about popular culture events, and one of the things he mentioned was Star Wars, which made me want to contact him, and he gave me a link to his hour-long YouTube presentation, We Need Our Space, which is all about the worlds within Star Wars, and he gave me permission to share it all, and when you get the slides, the URL should be there. Next. I also used a Wikipedia list of all of the Star Wars planets and moons because there's a lot of them. Jay's original hour-long talk was just about the first 6 Star Wars movies, and I wanted to expand it to all 9, and I can't remember things. Next. On Earth, the planets of Star Wars all have one climate. Of course, on Earth, things have different climates, as well as the planets and moons of our solar system. And everything, of course, was filmed on Earth, so everything really could have been on Earth. And I wanted to start with planets very similar to Earth next. There's Kashyyyk, which is the planet of the Wookiees, Alderaan, which is the planet of Leia, Princess Leia's homeworld. There's Dagobah, where Luke met Yoda, and Ahch-To, where Luke retreated. Next, went into exile. Takodana, which was Maz's castle's place. Endor, which is home of the Ewoks. Kijimi, which was ultimately destroyed by a Death Star, and was where they found coordinates to a wayfinder, and Dakar, which is where a resistance base was. All easily could be been done on Earth. Next. So planets that look like Mars, there's Geonosis, which has a dusty surface eroded by water, much like Mars, although it has rings and moons, which we could just add Saturn. So between Mars and Saturn, we could absolutely picture Geonosis. Next. And then we also have Jakku, which is Rey's homeworld, and Pisana, where Rey finds a dagger with Sith text, and both of those look very dry and arid, perfect for Mars, although Mars is very cold, and these were both kind of room temperature. Next. And Jakku was filmed in the UAE, and Pisana was filmed in Jordan. These are pictures of both of them, and both of them could be Earth, but Mars seems very dry and would be better, I think, even though it's cold. Next. And then there's Cantonica, which is the planet where the Canto Casino and Racetrack is located, which is also very arid. Next. And Crete, one of my favorite planets. Crete has a white, salty surface, which the Star Wars creators said that it was salt, and underneath it is red soil, ruby red soil, which is kicked up. Next. And I thought that Mars would be perfect for this because we have found salts on Mars, including halite, which is table salt, although although it's not so thick. And where Crete is ruby red, if there were oxygen on Mars, the color would be enhanced. And this is Victoria Crater on Mars, which is one of the places where halite has been found. Next. And now Naboo. Queen Amidala was queen of Naboo. And above ground, Naboo reminds us very much of Earth. It's kind of swampy like Georgia or Louisiana. And the capital city of Thebes was inspired by Seville, Spain, and filmed in Seville. Next. But underground, Naboo is a lattice. It doesn't have a rocky core. It's just water all the way down, a lattice of water. And that Earth would not be a good fit for the interior of Naboo because our oceans are only 7 miles deep. Next. So I was thinking about Europa. Europa is Jupiter's moon, which has underneath its icy crust a thick worldwide salty ocean, which we're hopefully going to be investigating soon. And it also could be made warmer through tidal flexing. Next, Mustafar. Mustafar was the site of the final showdown between Obi-Wan and Anakin, and lava and volcanoes are everywhere on Mustafar. Next. And the most volcanically active place in our solar system is Jupiter's moon Io, and the picture on the left shows all of Io, and the picture on the right shows one of the volcanoes on the limb, and there are 7 or 8 active volcanoes at any time on Io. Next. Are there exoplanets that are like Mustafar? It turns out there are many of them because they're, oh, thank you. And UCF 1.01 is one of them. Next. And Kepler 10b is even hotter, and Corot 7b is even hotter still. And all of them are orbits their star very close. Next. The Death Star looks like Saturn's moon Mimas, and in the middle is Mimas with its crater Herschel. In the left and right are the 2 Death Stars, and the Death Star was actually seen by Voyager 3 years after A New Hope came out, so it's just a coincidence. Next. Hoth is a snow and ice-covered moon or planet. Next. And Enceladus is the things fall back on Enceladus as snow, so it could be a good substitute for Hoth. Next. And finally, there's an exoplanet with a long name that was discovered using microlensing that sometimes they call Hoth. Next. Utapao is a place with worsening hyperwind storms, so the residents went underground. Next. And Iapetus might be a good place because they mined underneath it for water. And next, and Neptune is the place in the solar system with the fastest winds. So maybe Neptune as well. Next, Bespin or Cloud City. Cloud City. Well, next. I have a lot. Venus might seem like a great substitute for Cloud City, but the clouds of Venus are full of sulfuric acid, so no. Next.
You're very close to time, but if you want to forgo doing the Q&A.
I probably do, but thank you. And everybody can see Tatooine has 2 suns, and it's circumbinary, which means that the planet orbits both suns, and we see a lot during the Star Wars saga, home of Luke and Anakin. Next. And it's going to need an exoplanet. Kepler 16b is the first circumbinary planet that was discovered, although it's not within the star's habitable zone. Next. Kepler 453b orbits 2 stars, and it is in the habitable zone. Next. Coruscant, which apparently I mispronounced, but it looks like Coruscant to me. It is a planet that has just one big city throughout the entire planet. We spend a lot of time there in the first 3 films, and it has apparently 2 trillion inhabitants. Next. Kepler 452b is sometimes called Earth's cousin or Earth 2.0, and it orbits a sun-like star, and it is 1.6 times Earth size, so possibly it could hold 2 trillion inhabitants. Next. Cabino is an ocean planet where an army of clones was discovered. Next. And Kepler 22b might be an ocean planet. It might be gaseous. We just don't know. Next. Yavin 4 is actually a moon that orbits a very large planet called Yavin, and you can see it's a red gas giant planet. Next. And this is my final slide. Exomoons. Endor is a moon too. We have some exomoon candidates, and we have not really found any exomoons, but Webb hopefully will figure it out. Some exomoons are in rogue planets too. The micro lensing works with that, and that is really all that I have. Thank you. And thank you for doing that.
All right, so thank you very much to Carol. And next up we have Oana Jones from Canterbury University. Okay, is yours on here? All right, and then I'll just be right over here. I'll signal you for 2 minutes.
Great titles.
All right, kia ora everybody. I'm just going to get started as you're sitting down. So today I wanted to talk a little bit about space and time, and I know we all had a really good time at Hospitality Suite last night. I was there till stupid o'clock in the morning, and they asked me, what are you doing in the morning? And I'm like, I'm just talking about relativistic time dilation for toddlers, so that was a great life decision on my part. Anyway, I'm going to power through this really quick. So it kind of starts here. I'm kind of drawn to things that I don't really understand. I like asking stupid questions and generally not knowing things. And one of my favorite concepts to talk about in the planetarium is time dilation. And the reason I like that is because, number one, it sounds cool. Number two, it is cool. And number three, I want other people to know about it. So when working on a live planetarium show, I like to include it, and what I used to do is give a couple of examples. Now, the most obvious place to start is simply to look up at the night sky. When you look up, we say that you're looking back in time. You've got a giant time machine. We know and often say that nothing can travel faster than the speed of light. And we talk about how gravity affects everything, including light and including time. So we've got a couple of examples we use. The first one's about the ISS, so the faster something moves, the slower time seems to go for them. So these are the astronauts, Scott Kelly and Mark Kelly, who spent some time on the ISS. This was an experiment that was done. Scott Kelly was already 6 minutes younger than Mark, but after 11 months in space, he came back 6 minutes and 13 milliseconds younger than his brother. So this also affects us every day. So we talk about GPS satellites and how they use atomic clocks to help them know all about what time it is and be able to calculate where they are, just like navigators in big sailing ships used to do. But atomic clocks need to tick slightly slower to stay in time, so compared to Earth-based clocks. And they have to be set incorrectly at launch to account for their flight into space. So without this adjustment, problems with your GPS would begin after about 2 minutes. Then we'd drift further out at a rate of about 10 kilometers a day if we didn't account for time dilation. So this is all kind of cool. And with these two examples under my belt, I was feeling pretty confident, overconfident. But I thought I could explain it to a general audience. Boy, was I wrong. I used this example. So I used the example of flying to Alpha Centauri. And I said if we were to travel at the speed of light to Alpha Centauri, it would take us about 4 years to get there, 4 years to get back. So 8 years for us, but for other people, 50 years or so would have passed on Earth. Who's used that example? Can I get a show of hands? Cool. Before I say anything else, the statement I just made is wrong, okay? I did a thing where I memorized half a fact and I used it so many times that it kind of got warped beyond meaning. I can't even find the original source of the thing that I just said. And from your show of hands, a couple of you have used that exact same fact. And it's an example I just don't use anymore. But the concept of the speed of light being a hard limit is still true regardless of how awful and wrong my example was. I don't like people telling me that things can't happen. I don't like being in my planetarium and being able to fly from Earth to the center of Sagittarius A and tell people that I can do it in my planetarium in 30 seconds, but actually it's not possible to do. That really bothered me. So I came up with this. If I can't travel from Earth to Alpha Centauri in 30 seconds, why can I do it in the planetarium? Why can a planetarium visualize it? And this bothered me a lot. Like everybody does nowadays, I did my own research online. That was great, but I didn't really understand it. But I did have two things that most people don't have access to. The first thing I had was a track record for asking stupid questions of smart people and having absolutely no shame. The second thing I had was smart people that I could ask stupid questions to. So this is Professor Jörg Frodliner from the University of Otago. He's a professor of mathematical physics at the university specializing in gravitational waves. And I figured if anybody could tell me about space and time, it would be him. And he did. He explained it very, very succinctly. Unfortunately, I didn't understand what he said. He wrote me a mathematical equation and I didn't know how to read it, so that was great. Luckily though, I had a second thing most people don't have access to, which was different smart people to interpret back to me the things that I don't understand. So this is Andrew Charlton. He's a developer that I worked with at the Otago Museum, who has a wealth of experience in software and has been putting up with my nonsense for about 7 years, where I come up to him and say, I have a really cool idea, and he has to make it happen. So between two experts and an idiot, we figured out what we were going to do. So what we came up with is a couple of things to understand. So space and time are relative and connected. Your experience of time is affected by your velocity, so how fast you're traveling. Your head is older than your feet, which is due to gravity. Space and time are relative to your frame of reference, which means every person experiences space and time in a slightly different way. Between you sitting next to each other in this room, it doesn't make a huge amount of difference, but the faster you go, the more mass you have, so lots of things change when you start getting really, really quick. At light speed, you have infinite mass, which means you have infinite energy, which ruined my time travel fantasies, but nonetheless. So what I wanted to do was be able to explain this concept to toddlers, or near enough to toddlers. So we have a science show that we used to run in our dome, which was part planetarium show, part science show with experiments. And I wanted to show toddlers how time can change depending on the way that you fly through. And to make things harder, I didn't want to do this in a pre-recorded show and calculate it out. I wanted it to work live. So we used Digistar in the dome and we came up with this. So this is a live, sorry, it's a little bit small on the screen. This is a live display that we came up with in Digistar with 3 clocks. So on the left-hand side is the is the time on Earth. In the middle is the time on your spaceship, and those two things start exactly the same. On the right is the time difference. So what that does is it tells you how many more times faster is spaceship time compared to Earth time. Does that mostly make sense? Cool. Now, because of the way that Digistar works, we were able to get 2 important pieces of information from it. The first thing we were able to do is figure out how fast we were going. So the camera in Digistar knows its velocity. So by using the velocity, we were able to calculate the time dilation of the camera as it was traveling through space. And then the second thing that works really well is in Digistar, massive objects like black holes also specify their mass. Anything smaller than a black hole doesn't really affect time dilation enough to be affected in this show, but black holes do. So luckily we had both of those two things, which was really, really cool. So Digistar code accounts for both the velocity and the mass affecting time dilation, which is just how it would work normally in physics. You have a mass calculation, velocity calculation, and you get realistic time dilation, which means with your clocks up, you can now open up Digistar and go from Earth to the center of the Milky Way galaxy in 30 seconds and show exactly how that would affect time. Because it is possible to go from Earth to the center of the Milky Way galaxy in 30 seconds, and the thing that I didn't appreciate is the faster you go, the more time slows down for you. So when you get to the speed of light, it's instantaneous travel. And as you get close to the speed of light, you can actually do this. So you no longer have to tell everybody in the planetarium that you can't travel from Earth to Sagittarius A in 30 seconds, because you totally can. Now, this script is currently set up for Digistar. It's on the Digistar cloud. It just works, click and go in Digistar 7. If you swap to Chakra Core, you can actually run it in Digistar 6 as well. But I would love to port it to other platforms. It's completely free. If anybody would like the code, come see me, I'll give it to you. I'd love to see it in planetariums and see you guys using it for really cool relative time stuff. So lastly, how do we get back? So after we've gone to the center of the galaxy and come back, the sun is now a red giant. And we do show that on the dome, that the sun is a red giant, and explain how that works. Well, at this point, science fact turns into science fiction, and thanks to the team at the ESO, we have a conveniently placed wormhole that takes us back to Earth for our children. So here it is on the Digistar cloud. You can just download it from there. It's got a little control panel, so you can also pause time, reset time, and I will be adding in so you can set the time to a specific one, which is useful if you're trying to display a certain point or make a certain point. Questions? I think I've got time for 2.
One can keep in mind, like Einstein said, that we should explain something as simple as possible, but not simple.
Yeah, you should explain things as simple as possible, and I feel like I am a blank slate for explaining concepts too. Any other questions?
I try to remember his name now, but was one very, very clever physicist about time being relative, but he preferred to say it's personal.
It is personal. That's
so
good.
That's something you can think about, that somehow it is personal, but the relative velocity of the people makes that each have.
Yeah, to the frame of reference. Thank you.
So, but it was a brilliant idea to work on this.
Thank you. Yes?
I was just wondering if you've ever considered putting ages in there to have fun with it, not just the time difference.
Ages, as in epochs?
No, as in a human. Here we are, you're 10 years old and we're starting.
Oh, I mean, maybe if you travel around the solar system, but the thing is, from here to the center of the Milky Way, 50,000 years goes past really fast. So it didn't really seem that relevant. Yes?
Do you plan to, or have you shown this program to middle school and high school ages yet, or to universities to share?
Yeah, so we've run it in our public programs that are just general audience. We've run it in our kids' shows. I haven't run it with university students, but I have shown it to university professors. I would love to see what you guys do with it and hear what you guys do with it if you decide to use it. Have I got time for one more?
Yeah.
Anybody else? Yes?
So when you're working with younger students and they start asking you questions, do you kind of try to angle it more towards open-ended questions?
Yeah, generally. Even if they don't ask an open-ended question, you answer it as if they did, which helps a lot. I find the smaller ones have better questions than the older ones who are maybe a bit jaded. Yep.
What's it called in the cloud when you're looking it up?
Yep, so it is called Time Dilation Controls under Canterbury University. Any other questions? And I'm on time.
Thank you.
Thank you.
All right, so up next we are going to have Masie from Creative Planet, and we'll get set up and get started in just a minute here.
Yeah, this headphones, so it's okay. It's okay. Hello? Should I take it? No, maybe not. So, my name is Maciej Ligowski. I'm a Full Dome Show producer and director. I started my career in Copernicus Science Center in Warsaw, where I produced my first show called Dream to Fly. And then after organizing IPS in Warsaw, I decided to start my own company and produce the Full Dome shows. Oh, and I did that. Full Dome films ever since. So today I'd like to share some thoughts I have after almost 10 years of experience of doing that. So, but I like to start with a question like, what a planetarium means for you? What is it for you? As a venue?
It's an immersive space.
Immersive space. What else? Oh, come on, you're working like so many years. Just shout.
Entertainment. It is a starship.
Starship.
A magic trick.
A magic. You see, if I think about planetarium, I see a concert hall, and I see a lecture hall, and I see a theater, or even, you know, wedding hall. Like, I've seen weddings in the planetarium, which are cool. So when I think about the planetarium, I see a multi-purpose venue. And it's important for me to stress that in my mind, that this purpose can change very quickly, like even without one show. If you look at these pictures, there's a common thing for me in all of these situations. There is an actor on the stage. And with exception of maybe a laser show, if I think about show, I usually tend to imagine an actor on the stage performing something, a dancer, a singer, or even like a lecturer, right? He's giving a talk. But when I look at this situation, it's quite different. For there is no actor on the stage. And what I see here is a sequence of images accompanied by sound and the dialogues or a narration. And by definition, for me, it's a film. It's a visual artwork that communicates ideas or stories through the sequence of moving images with the sound, with the dialogues. And so if we go back to that picture, I don't want to say that your audience is not coming to experience a show. Yes, there are many times coming to experience a show. There is a live part. There are questions at the end. It's a show. But the moment we press play on the console, we turn planetarium into a movie theater. There is no actor on the stage. There is no live performance. There's just the movie. And I strongly believe that what we show at that moment should be a movie. It should follow some basic concepts. So now we come to a question, which is very important for us. How to make a good planetarium movie? Well, it really depends who you ask. Like, we get emails which are quite opposite. Like some people will say, oh, I absolutely love the ending of Magic Globe, that it's open and you ask the girl, you ask her to figure out the answers by herself. And some people say, oh, it's so confusing for kids. Like, it's obvious that we cannot please everybody. But what we try to do is to simplify the problem, and to do that we group all of these requests and demands into some understandable chunks. So of course it's easy to put a dot somewhere in this triangle and say, oh, that's the compromise, but it's much harder to do that. And the second thing, of course, each producer, each director will have his own path to achieve that goal. What I can do, I don't know if I should, that's a secret. But what I can do is to share with you how we do it, how we approach it. So for me, the most important part is that the idea that we don't have to reinvent the wheel many times, right? So, of course, we are working in much different environment, and the purpose of our movies is completely different. Like if we go to cinema, it's just for entertainment. If we go to planetarium, we expect that there will be some science taught to us. But still, these are films, and they should follow, in my opinion, they should follow some basic cinematic concepts. A story. I believe this is what keeps the kids and any audience involved. Like, if there is no story, after 5 minutes, they will be thinking about shopping next day. And even if it's like off narration show, there can be a story. Like one pattern, for example, is that we show the history of development of anything, like automobiles, right? Then we show that's the history, like how it was developed over years, over decades. And then we have stories of individuals, I don't know, Ford, right? So we can jump from story to story. If we add some facts about his life, it gets more and more involving. And, what story also gives you is that our target groups are very wide, and we must accept that there will be times that somebody will be lost. He won't understand what was said, but the story will keep him involved, and then he can come back. If there is no story, he's lost. And I believe emotions are the best way to memorize something. So if we go through emotions, yes, they will remember that. So how we can merge the story with science? This is our idea. It comes from my conversation with my son. We were driving, and he started, like he was 11 or so, I don't remember exactly, but it was many years after he saw Pixar Cars, and he started to I realized he remembers the plot. He remembers what the movie was about. 6 years later, he really remembered that. And that thought came to me, like, why don't we make a movie about something I want him to remember? So if the main dramatic problem is what we want them to remember, that it will happen. Because I don't think they will forget what the movie was about. We can forget some facts, some history, some plot facts, but we won't forget what the movie was about. And the second thing, if the story is not like merged with the science we want to teach, then the science is very distracting, and we lose their attention. It's still difficult with kids. Even they are very sensitive to teaching, and I heard that they get distracted still, but at least we're trying to get them more and more involved. So I got some emails about Magic Globe that there is too much story, and it would be nicer if it was more science oriented. And I calculated that. There's 19 minutes of pure teaching there. And I think like okay, it's a long show, it's more over 30 minutes, but to keep 5-year-old kids paying attention to 19 minutes of talking about astronomy, I think it would be hard to achieve that without the story, without, cheating them. So that's the topic of my talk. The model we try to follow, if we want to teach something more difficult, is to break the science into chunks, and that gives us many things. First of all, we can repeat things, right, to help them memorize. Second, we can break the science to chunks which are harder and harder to understand. So the little kids will, for example, understand first 5, and they won't understand the most, I'm finishing. They won't understand the most important, the most difficult parts, but they will still stay involved because there is a story. So I can show you just one short example, if I...
What is that Edmund up to? He's going to miss dinner again.
Uncle Edmund's here too?
Yes, he's rehearsing for a new role. He'll be with us all summer.
Oh, Grandpa, how long will summer last?
Well, astronomically speaking, summer lasts 3 months.
So,
after summer...
Maybe I'll mute it. So in this, it was important for her, for the summer to end, and she wants to know how long will summer last. So it's legitimate that he explains that. And if the kids follows the story and, have a connection with the character, he also wants to know, or she wants to know, why the summer lasts so long. So, going back to that triangle, we try to find a compromise somewhere. It's, again, it depends who you ask where the compromise is. We do it our way, and I encourage anybody who is thinking about producing shows to find his own path and own way. But my message is, please don't forget about the story and the storytelling, and please don't forget it's a film. So thank you so much, and I'll be very happy to talk about it more with you and hear your thoughts and feedback. Thank you. Yes.
So the important thing was to make the scientific question the question of the character.
Please use the microphone for accessibility. Please use the microphone for your question.
Oh, sorry. Yeah, so the clever idea was to make the scientific question the question of a character in the story.
Yes. To merge that as much as possible.
You use the word story a lot. Do you want to give us a very short definition of how you make something a story rather than just talking?
Oh my God, that's a question. I would say that's something that, that will impose some emotions, right? Some anxiety, like I want to know what will happen. The feelings.
Which comes first, the story or the science?
I think the story. I think the story because that will make, Oh, that's another difficult. I don't want to talk too much. It's just that the story will cause emotions and involvement, and I think we are more supposed to inspire. There's just that much we can teach in a half hour, but the story will give us opportunity to involve them, to make them like having good memories and feelings about that subject. It can be like Dream to Fly is a story like of narration, right? And it's very emotional. So people will be maybe interested in the subject afterwards.
You said yesterday that you had introduced a conflict, and since you yourself have a doctorate, you were like, oh, it's a totally unbelievable scientific conflict, but it was necessary for the excitement in the story. So that may be part of what you were going to say about the story.
Yeah. So yeah, it's really a struggle also for us. I don't want to say we have all the answers, and we're very far from having all the answers. And we're trying from movie to movie. We're trying to learn and develop new ideas and the workflow. It's very difficult. That's maybe the most difficult part. Basically, it takes us 2 years usually to write the script. We change it and correct it many times. Too many. Thank you so much. Thank you.
All right, so now for our final presentation of this session, let's welcome Dana from the Charles W. Brown Planetarium at Ball State University.
All right, good morning, everyone. I'm Dana Thompson, Planetarium Director at the Brown Planetarium at Ball State University in Muncie, Indiana, and I use she or they pronouns. A little bit more about myself. I am a planetarian. I have a love for science, both natural and social. I have a master's in physics. I'm a creator. I've created a number of planetarium programs and experiences. I'm a daughter, a sister, and an aunt. I'm a roller derby player. I'm a cat and a dog mom, and I thought the new Scream 6 movie was pretty good. But I spend a lot of my time at the Brown Planetarium, which is the largest planetarium in Indiana at 16 meters across. And we usually welcome people into a small lobby. For being the largest planetarium, we do have a relatively small lobby, but we're able to bring out like an activity station when we have events. We welcome people into the main event, which is the planetarium experience. We do a program with them, and then they pretty much leave. And really our mission is to lead people to moments of wonder. We have these shared experiences where we hope people feel a sense of awe. And whether awe is conjured by stimuli that are small and ordinary or large and complex, the emotion kind of falls under two major themes: being drawn away from oneself in the presence of something vast, and the need to be good unto others. So studies have actually shown that people, after experiencing awe, will interact with the world with greater generosity, ethical decision-making, and pro-social values. So one of the things I kind of like to joke about is if you want to really inspire people and benefit from it in your planetarium, because we always invoke awe in the planetarium, is to have a donation box in your planetarium, because people are more likely to donate to a cause after feeling emotions of awe. And we do actually do well with our donation box in the planetarium. But awe helps us basically it brings us into social networks, communities, collaborations, and groups where a person can really become active in ways that benefits others, the larger circle. It basically shifts us outside of our own interests and into the interests of other people. And when your attention is directed outward due to these feelings of awe, we have this sense of small self, usually, and this is referred to as the small self. And when we display these visuals that are really vast and large scale in the planetarium, we can really make a great impact and elicit these feelings. But it's not always so easy. It's not a one-size-fits-all when we talk about awe in the planetarium. People can experience awe via many different stimuli, based on and shaped to their backgrounds, their norms, their values, their cultural beliefs. And so our efforts to induce awe can really be broadened to appeal to a larger diversity of audiences by taking their cultural backgrounds into consideration. And I think that the planetarium field has been doing this more and more each year. I won't go too much into that today, though. Really, I want to talk about how we expand beyond the dome and are bringing some of these large-scale images out into our planetarium lobby, which is a little small, a little sparse. So we got funding from the IMLS to expand our engagement opportunities through space and time. And we're wrapping up that funding cycle this year. It was a $50,000 grant, and on it we purchased a new solar telescope, a Coronado Solar Max 3 90mm telescope, and purchased a nighttime telescope while we were at it, got some computerized mounts for them, and then I put them on these tripod studio dollies, camera tripod dollies, for easy setup for our students. To just roll out into the planetarium walkway outside and set up easily. And then there's a laminated guide down here, and that guide tells the student how to set it up after, of course, orientation with the telescopes, and it gives them a reminder so that they're pretty self-sufficient with these. And then we kind of moved into some exhibit design through the grant. So the grant helped support the telescopes, expanding exhibit design in the lobby, travel to conferences like this one, professional development, and then also some show purchases. We purchased Birth of Planet Earth and Living Worlds, which we are loving. So we created these banners here. They're magnetic banners that are modular, so we can pull them apart and put them together for photo walls and stuff like that. These ones particularly were designed with the help from communications in the university, but the rest of them I designed here. So we had originally with the construction of the Brown Planetarium, which was built in 2014, the Hubble Carina Nebula here. And it didn't have any description, and when we are trying to evoke these feelings of awe, we really need to explain what people are looking at and the scale to really make them feel that kind of sense of vastness and that small self that I mentioned before. So having some information about it was important here. So one of the first things I did off the grant was just design this little banner that explains information about the Carina Nebula and gives them a activity to do, so find the features, and then includes the new JWST image of it as well to keep it current. So the little find the features activity, just 3 of the 6 here, has them find that Bach globule, the caterpillar, some star clusters like Trumpler 14 there, and then some Herbig Haro objects too. But one of the cool things I did, and that I'm pretty excited to talk about, is the designs of some window clings that I have. So just what you're looking at here, when people enter the planetarium, they come in through the main entrance, through a vestibule, past these windows, through these doors here, and then there's additional windows there. And so just to design this, I took pictures, stitched them together, and I was trying to think of what could go on these to make them more exciting, and also kind of to block out some of the sunlight coming through when we do some activities that need a little bit more low light level. So I thought it would be really interesting to talk more about the electromagnetic spectrum and highlight the colors of the rainbow. So finding some large-scale imagery to do this was easy at first and then a bit of a challenge. So I went to different websites to search, and the Noir Lab and ESO have this search engine where you can search by color down here, and then a lot of other search terms as well. Google has this too. You can go under tools, you can sort by resolution, color, but you type in nebulae or nebula and it gives you this information. What I found most successful was just going to good old Google and typing in red nebula, and the first one that popped up here was the Lobster Nebula, excuse me. And that's an amazing image right there. I was really happy when I found it. I was like, oh, this is going to be a cakewalk. These are going to be wonderful, easy to find, and red was the easiest, and everything else took a long time. So the Lobster Nebula, you can read more about it, but if you don't know already, I will go over. Thank you. If you don't know, it did come from the dark energy camera that is on the 4-meter Blanco telescope in Cerro, Chile. And it's a 570 megapixel CCD camera. 570 megapixel, that is 570 million pixels. To put this in perspective, the average computer monitor contains 2.07 megapixels, 2.07 million pixels. Our planetarium domes at 4K is 16 megapixels, so 570 is a lot, right? So, of course, I didn't need to use all of the image for the window. I cropped it down, but it did make for a great image to start with. Then I got the Elephant's Trunk Nebula. Lower resolution, but still great enough to put on the wall window. The surface of the sun looks great too. Cass A was green, the Pleiades for blue, and I did get an 100 megapixel image from David DeMartin. The download link wasn't active, so I did have to email them individually, and they were really responsive, so kudos to them. And then the Orion Nebula in UV was purple. And so how did I actually get them onto the walls, windows here? So I took the images into InDesign, and in InDesign you can separate it by pages here. So here's a close-up. So there's these pages, and of course this is rotated clockwise 90 degrees. And you can put the dimensions here of the window. So 11 inches by 30 inches for the bottom frame. And then these pages are separated by the gap of the support structures so that there's not any jump in the images. So that's the preview there, right? Going back and forth. And then the install. And then up close in the vestibule here. So back to that. And then these do look really great in the dome. When we bring in them into the dome, of course, they always get a reaction, but this one in particular gets a wonderful reaction. We always hear gasps from the audience. Psychologically, gold is a color of motivation, and I think that kind of speaks back to awe. And there's this great quote, "Awe is a reminder that I am alive in a universe bigger than myself." It's pretty good. I wrote it. So, big, right? Scale of the universe, but also inner scale and scale of our community as well, right? So awe is a prompt for me. It's motivation to be an active part of our world. So thank you. A lot of great references about awe. I'll maybe do a paper in the IPS about this, or the planetarium, excuse me, and then my contact information.
each one of those images had vastly different scale. Did you do any, were you able to kind of do anything to try to help the audience see how different the scale on those images was? Does that make sense?
Yeah, that's a great question. So my talk was originally 55 slides. I cut it out. I deleted it completely. Okay, so there's future work for this. Sorry, it's not showing. There's some future work. I'm going to do another floor banner for this and talk more about the images, and then give some information about what they're seeing, because obviously it's not all visible, like the sun's in IR, and there's a lot of different components to be taught with it. So not just scale, but then information about the EM spectrum as well. So I am doing a floor banner for this as well. Any other questions? Okay. We are going into a break too, so if you want to chat with me, feel free to.
So that was the last presentation for this session. Thank you to all of the presenters and everybody else who was working to make sure everything was functioning for us here. So we'll see you guys back in a bit. Lost the mouse here.
Where did it? Oh, I wonder if it went onto the.
I think it did. Oh, there it is. Okay.